Go. Everybody say hi, Kelsey.
Hi, Kelsey.
Hi, Kelsey. Let me see if I can get this off the screen now. No? 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 I don't know. It'll go away eventually. All right. We just got done yesterday creating our very first frequency table. How exciting. How exciting. And it was kind of a pain in the butt, but, you know, it was pretty fun.
When you can color code.
Okay, sure. Categorical data, though, on the next page, they're going to introduce us to another type of frequency table that we won't deal with a whole lot in this class, but these are frequencies according to how many are in each category. So this is emergency room visits for injuries from sports and recreation, okay? So these are how many people visited the emergency room in a certain period of time based on these sports, okay? So bicycling sent 26,212 people to the emergency room. Football was the next highest, was 25,376, and so on and so forth, okay? This is categorical data because we don't have classes. Well, they are classes here. We still have classes, but they are not a range of classes. They are like the category. Like we could do this for eye color and tell the frequency of the number of people that have a certain eye color, etc. Right? These are all. Do those results surprise you? Like look here, look down here at the bottom. ATVs. They're the lowest category. I would think they would get more than everybody else, but maybe like they're not as frequent. Less people have maybe ATVs. I don't know. Playground. What?
Most Altarians do.
That's true. There are seatbelts. So anyway, I don't know. Some of these kind of surprise me. But maybe like bicycling is the most frequent. Like everybody has a bicycle. So maybe that's just because it's more. What? Right, because you gotta take your 4-year-old to the emergency room every time they fall off their bike, So this is the categorical data for frequency table, okay? We won't see a whole lot of categorical frequency tables, but they're just saying that is a possibility, okay? All right. Now we have 2 more columns that we could add to our table. There's a column for relative frequency distribution, and there's a column for cumulative frequency distribution, okay? So relative, like if you think about your relatives, you are in relation to the people around you. Like your relatives are the people around you that you are related to. So relative to the total, I'm going to say relative to total. Relative to total is what that column consists of, okay? So what I mean by that is relative frequency, okay? We are talking about time in seconds. This was the table that we built yesterday. We had 11, 24, 10, 3, and 2. Same numbers as we had yesterday. And these are the seconds, the time it takes in seconds for McDonald's to bring me my meal, okay? Was there 50 total? You have to know the total in order to do relative frequency, okay? So 50 total. This first category, relative to the overall, it is 11 over 50, or, can somebody give that to me? I guess percent. 20%. If you multiply it by 2, that would be 22%, right? Relative frequency is the frequency divided by the total, represented usually as a percentage. Sometimes they'll still have you represented as a fraction. On the homework assignment, make sure you look and see which one they are asking for. They will put that in the blue letters below, whether they want it as a percentage or a fraction, okay? Sometimes they'll accept both. The next one is 24 over 50, okay? Converting that to a percentage, it's out of 50. You want to get it to be out of 100, so you just multiply by 2, right? 24 divided by 2, or multiplied by 2 is 48%. 10 over 50 would be 20%? 20%? 3 over 50 would be 6%. 2 over 50 would be 4%. Okay? So either one of those, whichever way it asks for you to represent that data, relative frequency means in relationship to the total, what is the frequency, okay? So when we put it into those terms, I can see which one is the highest category based on percentage rather than the actual number, right? 48%, so just about half of the data is between the 125 to 174 mark. Does that make sense? We can see it in relationship to the total, okay? Cumulative frequency you're going to add each time. Add each frequency for the next value. Okay, add each frequency for the next value. Not in this class because we do a project for the semester test, but in all of my other math classes, I do a cumulative test, at the end of every semester, right? Cumulative means you're adding everything all together. So every one of the chapters that we had done in that semester, you're adding those all together. That's your cumulative test at the end, right? Okay. So cumulative frequency in relationship to these guys, okay? We start with 11, okay? 11 is still going to be the first category, but then we move on and we've added 24 to that. So my next number should be 35, okay? The next number after that should be 45 because we've added 10 more. Do you see where I'm getting these numbers from? No? No? Okay. You're just looking at each one of these individually. So the first number is 11. The second number is these two added together. The third number is those three added together. The fourth number is those added together. And the fifth number is the last one, right? So 45, the next one should be 48, and then we should be finally at 50. Okay. Now, here's why cumulative frequency is important or what it's useful for. If I say to you, how many orders were there below the 225 second mark? How many orders were below 225? 225 is here. How many were below those?
48.
I just look at this number right here. 45 were below that, right? It has it all added for you. Does that make sense? Okay. So that's a reason why that's useful. How many orders were below the 125 mark? Well, that's just the first category. That would just be 11, right? Okay. So looking at that, you can see how many were below a certain amount, and that's what cumulative frequency is used for. Make sense? Not too bad. Okay. All right. Critical thinking. Here we go. Frequencies start low, increase to 1 or 2 high frequencies, and decrease back down again. We will talk a lot about normal distributions. Circle him really, really good. So you make sure that you have your attention on him. Things are normally distributed if things in the middle happen the most often, okay? So for example here, this was the data that we had to start with, our 11, 24, 10, 3, 2, okay? But that's not necessarily normally distributed. They went ahead and showed us what the distribution would look like if it were normally distributed. What happens for normal distribution is the highest frequency is going to be the category that's in the middle. And then you kind of have your low frequencies here and your low frequencies here that taper off, because it's very rarely going to happen that you have to wait like 5 to 7 minutes for your order in McDonald's, right? That's kind of a long time relative to, some of these other data values. So that would be the low value that are high, right? And it's probably going to be pretty rare that you get in within like 20 seconds, right? That's probably not going to happen. Or even like 70 seconds, whatever. So the low frequencies are going to happen on the outsides, the very extreme numbers, a very long wait time and a very short wait time. Those are going to happen less often than the wait times that are going to be in the middle, okay? So this is normal distribution when you have 1 or 2 high frequencies in the middle and they decrease back down again on either side, okay? So if I would think about this like in a, like linearly, if we're looking at these data values, it starts here, it goes up, and then it comes back down again. Have you seen that guy before? You will see him a lot going forward. We'll do lots of stuff. This is a normal bell curve, okay? And normal bell curves are representations of normal distributions or standard distributions, okay? Does this make sense, or do I need to elaborate more? No? Okay, so starts with low frequencies, increases to high frequencies in the middle, and then decreases to low frequencies again, okay? All right. All right, let's talk about some weird things that happen every once in a while. Analysis of last digits, okay? I'm just gonna look at this table. This is a lot of stuff to read, but I'm gonna look at this table and I'm gonna see if we can figure out what's happening here, okay? Last digit of pulse rate. What is pulse rate? Your pulse. You're taking your pulse. You're looking up at the clock and you're taking your pulse and you're doing whatever, okay? So take a look at this. we had 455 people who had a last digit pulse rate of 0. Okay, that means last digit. So their pulse rate could have been 60, their pulse rate could have been 70, their pulse rate could have been 80 or 90 or maybe 100 if they just got done exercising, or maybe it's 50 if they have a really low pulse rate, right? Or maybe in the 40s, but not so often. Pulse rate's usually somewhere in those categories. Or if you're exercising, it could get up to like 140 or something like that, you know, depending on how strong your heart's racing. Okay, so that's what that means by the last digit being a 0. This is the last digit being a 1, so like 61, 71, etc. Right?
Yeah.
Last digit being a 2 would be 62, 72, etc. Last digit being a 3 would be 63, 73, etc. Do we get this trend here? Okay. What's something you notice about this frequency table?
All the odd numbers are low.
All the odd numbers are gone, right? We have nobody in the odd numbers. Now, is it probably the case that like nobody has an odd numbered pulse rate? Like if you take your pulse rate right now, I'm guessing we would get probably somebody that has a 73 or somebody that has a 77 or something like that, right? Look at your somebody look at your watch right now. What do we got? I got an 87 right now. 55, you're 77, right? So what the heck's going on here? Why are we not getting any odd numbers to show up on this table?
I have no idea.
You have no idea?
However you're measuring it, maybe?
Yes, how we're measuring it is hugely important, okay? So in the day before, like smartwatches, like did your whole pulse rate for you, okay? People would actually look at the clock and go around the clock for 60 seconds and they take their pulse rate, right? But what they're doing in this case is people don't want to waste 60 seconds, so they do it for 30 seconds and then double it, right? And when you double it, it's always going to be an even number, right? So they're only doing it for 30 seconds and then they're doubling it. Does that make sense? That's why we were not getting any odd numbers in this thing. So for us, that's hugely important because we know how this data is collected. Yeah? Are we okay there?
Yeah, I got cleared.
To play, right?
Okay, sure.
Nice.
Whatever. All right. So the fact that those odd numbers are out means we just did, so just measure for 30 seconds and double. And that will give us only even numbers. Do we see how that works? The day before smartwatches, you actually had to like measure your pulse on a clock. So they're doing just for 60 seconds, counting that number, and then multiplying it by 2. So really, your pulse is going to be off by maybe 1 or so for what your actual pulse would be in 60 seconds, but it's going to be pretty darn close, right? Okay, so only even numbers, we multiply by 2. Good? All right, let's talk about gaps in data. All right, the presence of gaps can suggest that data are from 2 or more different populations. So here's another thing that we could experience on a frequency table or see, okay? So taking a look at this, we're talking about what?
Weight of penny.
Weight in grams of a penny. Okay, weight in grams of a penny. So we've got like several of them here that are between, let's see, 2.4 and 2.6 grams. Okay, there's like 37 of them that are between 2.4 and 2.6. And then all of a sudden we have like none of them that weigh this amount, right? And then we have like several more that are between 2.9 and 3.2 grams, right? So like why are we not having any of them in the middle? What's going on with our collection of our pennies?
A number of them were made at like one point, and then like another group of them were made at a different point.
He's exactly right. A number of pennies were made at one point, and a number of pennies were made at another point. But what's happening in between those two?
A break.
We change the material that we make the pennies out of. Yes? Zinc versus copper, I think was the two that we had. 95% copper versus 5% zinc. And then we switched it, so we're now doing 2.5% copper and 97.5% zinc. And that changes the weight of the pennies, right? So if we're looking at this data, we might want to go through, and if we notice something like that, either do this group or this group and not both, right? Otherwise we're gonna get some weird numbers, right? Or like no data in the middle like we just did, okay? So those are things that we need to consider when we get a frequency table, okay? Make sense? That would happen, okay? All right, so our pennies heavier now than they used to be? Pennies made before 1983 were 95 copper and 5 zinc, but pennies made after 1983 were, I don't know which was heavier, which explains the large gap between the lightest pennies and the heaviest pennies. Which one's heavier, copper or zinc? I have no idea.
I think copper's
You
heavy.
think copper's heavier? So they would have been heavier before, now they're lighter?
Yeah.
Okay. All right, so I'm gonna put change in material that penny is made from. Okay, we changed the material that the penny is made from in those two time periods, thus the 0, 0, 0, 0 in the middle of our frequency table. Make sense?
Copper's denser than zinc.
Okay, gotcha.
That's fine.
So we have lighter pennies now. All right. Okay, comparisons. Combining two or more relative frequency tables in one table makes comparisons of data much easier. So now we're comparing McDonald's and Dunkin' Donuts. Who's a McDonald's person? Who's a Dunkin' Donuts person?
Coffee.
Who really doesn't give a crap? There's a lot of you. Okay. Anyway, all right, so according to this, so they took our frequency table, and now we have like two frequency tables combined into one, right? We have a McDonald's column and a Dunkin' Donuts column. Who is better?
At what time? It depends.
Who's better at time according to this?
What do you mean?
Dunkin'.
Dunkin', look at their frequencies. They're shorter. They're on the lesser time end. Does that make sense?
Yeah, but what's better?
But what's better? McDonald's is better than Dunkin'?
McDonald's.
Yeah.
I don't know.
Dunkin' Donuts are terrible.
But McDonald's doesn't have donuts.
Okay.
Okay.
So
They're not even comparable.
Right, they're not even
Dunkin' is
comparable.
like breakfast, and McDonald's
Dunkin's
doesn't have
coffee is
breakfast.
way too strong.
McDonald's breakfast is good
Whose
though.
coffee is way too strong?
No, yeah, McDonald's coffee is good.
every day. I'm pretty sure.
Mr. Uredale does?
I'm a
Every
McCafe
day?
man.
Silly. Silly. All right, so according to this, it says the Dunkin' Donuts service times appear to be lower than those at McDonald's. True? Yeah. This is not too surprising, given that many of the Dunkin' Donuts orders are probably for coffee and a donut. It's just like, here you go, right? Like we already have it, here you go. Versus McDonald's, there's a bunch of different orders that could be created, okay? So McDonald's is probably a little bit longer than Dunkin', right? Good?
Yeah.
Okay, is that it? Yay! Yay! Okay, so just to recap, regular relative frequency table. No, excuse me, regular frequency table. Then we have categorical frequency table on the second page. Then we have relative and cumulative frequency table. Then we have things that could happen or you could notice in a frequency table, like normal distribution. The last digit could tell you something, and gaps could tell you something, and then you can use frequency tables to compare. Okay? All right, your assignment is not posted. It's gonna post in like 5 seconds when I get back to my computer. Ready?
Ready?
Go.
1, 2.
Hey, don't give me that. Ever say bye, Kelsey?
Bye.